Hi everyone. So how's it going? First of all, let me welcome you guys to the Unacademy JEE English. This is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And on this channel, everything is being taught to you completely in English. So this is a series that I host for class 12 students. And today, the topic that we are going to cover is LR circuits. So before we get started with today's topic, let me introduce myself one more time for those of you who don't know me yet. So my name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and I've been teaching physics for almost 8 years now. And all this teaching so far had been offline, and from this year itself, I have started teaching online with on this Unacademy platform. So, as I said, I myself, as a student, was All India rank 447 and All India rank 192 in the two stages of the IITJ exam that I had taken, and I also qualified NTSC Stage 1, NTSC Stage 2, and I was in the top 1% in the NSCP exam, which you better know as the Physics Olympiad. All right, so again, I've already coached many students to top ranks in the JEE exam, both mains and advanced in the offline setup. And now I hope to continue doing that here online with you guys. Okay, so moving ahead. So as I said, before this year, while my teaching had been offline, I had to move online in this new situation that we all were forced to adapt in. So that is what you guys as students can also do. You can adapt, you can shift from offline to this online option and with the help of Unacademy subscription. So when you get yourself the Unacademy subscription, you get benefits like live classes where you get to interact with your educators on a regular basis. You have live polls and leaderboards in these classrooms, which keep them quite interactive and fun. You also have test series and analysis sessions, which keep you on your toes regarding your preparation in a JEE exam. Then you have live doubt clearing sessions, which again is a huge benefit. Uh, so as most of you must know by now that every fourth session in Unacademy courses is supposed to be a live doubt clearing session. So with Unacademy Plus, your doubts are always taken care of. They never pile up. So hello Pitesh. So how many drops you took when you were preparing for IITJ? Okay, one. I took a single drop. So I did not join any coaching when I was in class 11th and 12th. So in class 11, 12th, I was doing self-study. Okay, after that, I realized that if I get good guidance, I will be able to, do much better in my JEE. So that was when I decided to take a break and I dropped 1 year and I did coachings for 1 year. Okay, I hope that answers your query. Okay, next. So again, our academy platform, apart from all these benefits which I've already mentioned, is also providing you the chance to study from the topmost educators from all across India from the comfort and safety of your home. So make sure you are getting this subscription and benefiting from it. Okay. Now these are the ongoing plus courses which are made for JEE Mains and Advanced 2022 aspirants. So mainly based on class 11 topics. Hi Rajesh, how are you? All right, so these courses include one course, which is a detailed course on graphs, sets, and relations and functions by Abhinav sir. Then you have an advanced course on redox and equivalent concept by Rahul Kaushik sir. And I myself am taking an advanced course on mechanics. Apart from that, four more courses are available for JEE Mains and Advanced 2021. Again, all of them are being taken by the JEE English team. These courses are being taken by the English team. They include courses which are as follows. For first, I'm taking an advanced course on electromagnetism. So that will be covering complete electrostatics, current, electricity, and magnetism. And then there is a complete course on differential calculus by Abhinav sir. Finally, you have an advanced course on chemical kinetics by Rahul Kaushik sir, and you have a detailed course on optics by Murli sir. So how can you enroll in these courses? So very easy. Okay. So first you need to install the Unacademy app. Once you've done that, go to the plus section of the app, select your goal as IITJ and click on that get subscription button. Now, once you click on the get subscription button, you will be redirected to the payment page where you will realize that one, the fees of the Unacademy courses is kept very moderately priced. So any reputed offline coaching would charge you anywhere between 4 to 8 times this fees. Okay, so that is what you have to pay in any of the reputed offline coaching institutes. Trust me, I have been a part of offline setups for almost 8 years, so I know the kind of fees that students have to pay there. So Unacademy is providing you the same quality education from the same top educators at a very, very affordable price already, and this price will be made even more affordable if you use this code RD Live. This code will give you an additional 10% off. So if you like my lectures, if you like to enroll in my courses, then you can get yourself the Unacademy subscription and use this code to earn yourself a 10% off. Now, when you click on proceed to pay, you will also realize that you're given a lot of no-cost EMI options for any subscription that is for 6 months or more. Okay, so that will again help you ease that payment process. Okay, and also let me remind you that the Unacademy Combat is going on, and the next event of Unacademy Combat will be held on live on 22nd of November. So I hope by now you all know what the Unacademy Combat is. So you can enroll, register now, use the code RD Live, do well, and win yourself some exciting rewards and prizes. Okay. Next, if you're following us on the YouTube channel of JEE English, then you can connect with us on the Telegram app using this link. This will ensure that you are getting all the notifications of all the lectures and sessions that are being hosted on the JEE English channel of YouTube, and you won't miss a single one of them. All right, so finally, let's get started with today's discussion. As I said, in the last class we discussed about self-inductance and a new circuit element called an inductor. Okay, and we saw the characteristics of an inductor. We realized that inductor is nothing but a resistorless coil which induces a back EMF when the current through it is changing. So we also realized that the current through an inductor can never change instantly, right? And we had studied the characteristics of a purely inductive circuit, which included only an inductor and a battery. Today we are going to focus on circuits which will have inductors and resistors both. These circuits are called LR circuits, and that is going to be our focus today. So this is how a typical LR circuit would look like. Okay, any typical LR circuit would have a resistance and an inductor and a battery. So we want to study the characteristics of such a circuit today. So first we'll talk about the growth of current in an LR circuit. Suppose this was the circuit, you have an inductor, you have a resistor and a battery of V volt, and at t equals 0 you're going to close this switch and you want to study how the current in the circuit would grow. Okay, so how do you do that? Let's see. We will assume that at time t, assume that at time t, the current in the circuit, has become I, or is I, some I, and it is changing, it is increasing at a rate of di by dt at this instant. So at this instant, it is increasing at a rate of di by dt. Good evening, Rajesh Chandra. Hello, AP. How are you guys? Okay, so that is what we are going to imagine first of all. All right. Now, see, why would the current grow? We already studied the characteristic of a purely inductive circuit, right? Current through an inductor, we realize, cannot change instantly. If it cannot change instantly, you cannot have a current of V by R flowing in it instantaneously, though this coil does not have any resistance, so to say, but this can provide a back EMF, right? So this is the characteristic of this, that this element will not allow this current in the circuit to change instantaneously. So it will grow slowly from zero, as we had seen. In case of a purely inductive circuit, it grows at a constant rate and it can grow from zero to infinity also. In this case, obviously, that will not happen, and it will approach a limiting value. Let's try and get the equation of that. So at this instant, we can apply KVL equation. So applying KVL equation at this instant, let's see what we get. So I told you that KCL equations are always valid in any kind of circuit. So that is going to be a primary mode of analysis. Okay, I know that any kind of circuit, whenever I'm analyzing, one of two laws that will always hold no matter what are KVL and KCL, because those were based on fundamental principles of conservation of energy and conservation of charge. So those are fundamental principles, those will always be followed. So I can apply those equations anywhere. So here, since this is a single loop, so I don't need a KCL equation. All I need is a KVL equation. So applying KVL equation, let's see what we get. So at a particular instant, I have assumed that the current is I, and the rate of growth of current at this R is, at this instant, is di by dt, right? So if I start from here, so let's start from here and go around the circuit like this. So when I cross this battery, the change in potential would be plus V, because you're moving from the negative terminal of the battery to the positive terminal of the battery, right? Similarly, when I cross this resistance here, I am crossing it in the direction of the current, so the change in potential would have been minus IR. Similarly, if I cross an inductor in the direction of the current, then the change in potential will be minus di by dt. All right. Why? Because our inductor will apply a back EMF on the circuit. So let's make a note of that so that you remember that for future. So when we cross an inductor in the direction of current, what is the delta V that we will encounter? Delta V would be minus L di by dt. Right? We have already studied about this, that inductors offer a back EMF, and the back EMF would be given by di by dt, minus L di by dt. Minus sign is suggesting that it is a back EMF, it is going to oppose the external EMF, right? And the magnitude would be L di by dt. So incorporating that, let's write a KVL equation. So I can write plus V minus IR and minus L di over dt. This would be equal to 0. Right? That's what KVL tells you. If you go in a closed loop, then if you return to the starting point, the sum of all the potential changes would be equal to 0. Okay. Now let's integrate this equation and let's see what we have. So we will get V minus IR equals L di over d. Okay. So I can take out the I terms on one side. If I do that, then what I'm getting is I will get that di over V minus IR equals L d, dt over L. Correct. Now I will integrate this. I know that current at t equals 0 was a 0. Okay, that I have already assumed because at t equals 0 the switch was open. Okay, I just closed it at t equals 0. So the limits will be 0 to some I, and the time in which this has happened would be 0 to some t. Okay, at t equals 0, the current in the circuit was 0. At t equals t seconds, the current becomes I. So integrating this, what you will have is you will get minus 1 over R ln V minus IR. Right? This with the limits going from a 0 to I, and this would be equal to T over L. Correct? I hope everybody is following this integration. Now, what you will realize is I will take this term on the other side and I will realize that I am getting ln of V minus IR over V, and this thing becomes equal to minus R over L times T. Okay. So from here, let's see what I can see. From here, I can say that V minus IR equals V times e to the power minus RT over L. Okay. I hope you guys followed this. Or now I can say that I would be equal to V over R 1 minus e to the power of minus RT. Okay. So this is the expression that I'm getting for current. If I want to see this circuit, the graph of this current, how will this current vary? So if I want to draw a graph of this current, let's see. Let's draw ourselves two axes. On one axis, we can represent the current. On the other axis, we can represent the time. So we realize this is growing exponentially, and at t equals 0, the current is 0. At t equals infinity, the current will approach to V over R, which would have been the circuit current if the L inductor was not there, right? Now, in this case, we have assumed the inductor to be ideal. So this is an ideal inductor. Remember, this has no resistance of its own. Okay, so if this is a line, this is a line which is V over R, then the circuit, the current graph would have looked like this. Okay, it would have been asymptotic, would have approached the V by R limit at t equals infinity. Good evening, Amod Kumar. How are you? Okay, everybody followed this. So this is the equation governing the growth of the current in an LR circuit. So remember this equation. Now, does this look familiar? If you remember the equation of the growth of current or the variation of current in a RC circuit. I hope you realize in an RC circuit, what was the equation like? For RC circuit, let's remind you, RC circuit, the current would have started from V over R and it would have dropped down to zero. So I would have been V over R to the power of minus T over tau. We used to write something like this. The tau was called the time constant, right? And here I used to get such a graph. Okay, I naught 2, it will fall to 0. This is just opposite of that. There, the current at steady state falls to 0, right? I hope you remember that. And here, the graph that you're getting is something like this, okay, which can be expressed as I naught times 1 minus e to the power minus t by tau. So we are going to write a similar form of the equation, and then we are going to call L over R as our time constant. Okay, so let's write that. So it can also be written as I equals I naught 1 minus e to the power minus t over tau, and where tau, what will tau be? Tau is called the time constant of an LR circuit, right? And tau becomes equal to L over R time constant. Now, if you realize, how can you define time constant here? At t equals tau. At t equals tau, what will be the current? The current would have been the peak current times 1 minus 1 by E. So 1 minus 1 by E, how much will that be? You remember that? That was roughly 36.8%, right? I hope you remember that. You had two percentages. One was 63.2 and then you had 36.8. Okay, so you can verify that. That is not an issue. So let's just write that at t equals tau, or time constant is defined as, time constant can be defined as the time in which the current reaches 36.8% of the peak value. Okay. Okay, sorry, 63 point. Yes, it is 1 over 1, 1 minus 1 over E. Right, 1 over E would have been 36.8%. So at t equals tau, I would be equal to 63.2% of I. So that is how you can define the time constant. Okay. I hope you guys followed this. So this is the equation of the current. This is how the graph would look like. And what can you say from here? What can we say from here? You can say that at t equals 0, the inductor behaves as an infinite resistance. And at t equals infinity, or in steady state, that is what we call steady state, when the current will stop changing. I hope you remember what a steady state was. Steady state was defined as at a point where the things related to the circuit stop changing their value with respect to time. So here the circuit parameters would be the current. If the current stops changing with respect to time, or the di by dt also keeps changing, also stops changing with respect to time, it will become zero at infinity, right? That will be called the steady state. And at steady state, you will realize that an inductor will behave like a resistorless wire. This is just the opposite of how a capacitor used to behave. I hope you remember that. At t equals 0, a capacitor would behave as an infinite resistance, and at t equals infinity, at t equals 0, the capacitor would behave like a resistance less wire, and at t equals infinity, the capacitor would behave as infinite resistance. Right? In steady state, it does not allow any current. For inductor, in steady state, it can allow every current. So let's make ourselves some notes that also I don't know where. We have run out of place, but we can let's just write that little note here. Let's write ourselves a note here. This is important. So remember that at t equals 0, inductor behaves as an infinite resistance, and at t equals infinity, also called the steady state, it behaves as a resistanceless wire. Zero resistance. Okay, so that is something that you need to remember in analyzing your LR circuits. Okay, and this equation again, you need to remember this one. Okay, where tau would be L over R, and this is called the time constant of the circuit. And time constant is defined as the time in which the current reaches 63.2% of the peak current value. Okay. Next, let's talk about the decay of current. So, as I told you, what is the use of an inductor? Just like a capacitor, an inductor can be used to store energy temporarily, and that energy can later be dissipated across a resistance. So, in this case, you will realize that initially, you will see that if the switch is in position A, then the battery would have helped establish a current in the circuit. And after steady state, if you switch the position of the switch to position B, then what happens is that the battery is cut off. Now, what do you think will happen when the battery is cut off? With the battery connected, you will realize there would have been a current I like this. Now, even if you make that switch, I told you that the inductor has a property that it cannot allow the current to it to change instantaneously. If the inductor was not there, the current would have dropped down to zero instantaneously. This will not happen with the inductor being connected. The inductor will keep on making the current flow for some time. Okay, so that is the role of an inductor. It can act as a power source till the time, and it will allow the current to go down to zero slowly. It will not make it happen instantly. Okay, so let's write about that. When the battery is disconnected, the inductor behaves as a source of energy, or as a current source, or EMF source, as an EMF source, and does not let the current fall instantaneously. Okay, that was the property of inductors. Inductors cannot allow the current through them to change instantaneously. See, what will happen is, as soon as you've disconnected the battery, the tendency of the current would be to decrease. Now, as soon as the current starts to decrease, the inductor will provide a back EMF which will try to keep up the current. So, that is what is stopping the decay of current. It is not allowing the current to fall down to zero instantaneously. And let's see how that equation would be governed. So, once you've made that switch, so let's assume that that switch was made at the steady state. So assuming switch was made at steady state, I will realize that at t equals 0, the current would be I naught, which would have been EMF by R. Okay, at t equals 0, the switch is being made, and at this time, I in the circuit would be E by R, which we can refer as I naught or the peak current of the circuit, because the current will go on decreasing from here. Okay. So now at some time t, let the current in the circuit, let the current in the circuit be I at some time t. So we are assuming that in some time t it has dropped down to some value I. And now how we are going to analyze? Again, we are going to apply the KVL equation. Okay. Applying KVL equation, let's see what we will get. So I hope you are following everything that we are trying to say. I'm trying to say that when the switch was made, then the current, assuming that it was made in the steady state, then the current in the circuit was E by R. Now, when the switch is made, the inductor, presence of the inductor will not allow the current to drop down to zero instantaneously. It will require some time. The inductor will cause the current to decay slowly. It will provide some power and it will keep on the current flowing. So now we are assuming that at some time t, I have assumed that the current has become I and it is changing at a rate of di by dt. Okay, so we have assumed at t, rate of change of current, rate of change of current equals di over some di over dt. That is what I'm. Now, at this instant, again, when we will write the KVL equation, we will first cross the inductor in the direction of the current. So when I cross it in the direction of the current, what is the potential change that I will see? I will see minus dl minus L times di by dt. Then I will cross the resistance in the direction of the current. So I will see a potential drop of minus IR. So I can say the equation would be minus L di over d minus IR would be equal to 0. Agreed? So that gives me that minus L di over this R. From here, I will take all the I terms on one side and I get di over I equals minus R over L d. Now, I will integrate this and the integration limits I know at t equals 0, the current was I naught, at t equals p, the current has become some I. Okay, so here I will have ln I over I naught being equal to minus RT over L. So this gives me that I equals I naught times e to the power minus t over tau, where again tau equals L over, or this is the time constant of decay of current. Okay, so this is my expression for current as a function of time. So if you want to plot a graph, let's do that as well. Let's see how the current is varying with respect to time. So at t equals 0, it starts at I naught. This probably I naught. And here you have I. On this axis you have I. On this axis you're representing t. So this current would have fallen from I naught to 0 exponential. So this is the graph that you would have seen. The kind of graph that you would have seen. Right? I hope everybody followed this derivation also. This is an expression that you must remember. Okay. So I hope everybody is fine with this. Important equation. This shows you that the current will not fall instantly. It will take an exponential path going down. And for this time, you realize from this time, and when will the current go down to zero? It will go down to zero at infinity. So obviously, for this current that is flowing, you will realize something, that somebody is providing the power that will get dissipated across the resistor. So you realize for this entire duration, see, power will get dissipated across the resistor. Why? A current is flowing through the resistor, right? So if the current is flowing through the resistor, you will realize that it will be dissipating some energy. It will dissipate heat of I square R. Where is that energy coming from? That energy of flowing this current, and that energy that is getting dissipated across the resistors is the energy stored in the inductor. Okay. So when the current was growing, you will realize when the current was growing, what was the magnetic field associated with the inductor? It was zero. As the current grows, there would be a magnetic field that would have become associated with this, right? And you will realize, so it would have tried to oppose this change. So a magnetic field would have gotten set up. And you can realize, if you write these equations, you will realize that if you talk about power, or the all the sources that are doing work, so battery is doing work. So during charging, you will realize that the total work done by battery would be the in heat dissipated across the resistance plus half L I naught square. So how much energy does this guy store at the steady state? At steady state, this will store an energy of half L I naught square. Okay. At steady state, L stores half. We've already talked about this in the last class, right? Half L I naught square amount of energy. Now, when you disconnected the battery, you will realize that it is this energy that will get dissipated across the resistance. Okay, so here, if you realize that there would be some heat which would be getting dissipated, right? I square R. If you integrate I square R dt from 0 to infinity, it will come out to be half Li square. So it is the energy stored in the inductor that is getting dissipated across the resistance. So that is the role of an inductor. An inductor can, at a later point, behaves as a source of energy. It can help provide the resistance with the energy it needs to dissipate. Okay, so that is the entire aim, and this is how the circuits are analyzed. LR circuits are analyzed. If you have any doubt about all the discussion that we have had so far, then you can let me know. I will go over that one more time. So I'll give you 1 minute to go through everything that we've discussed so far. So this is the growth circuit, growth of current. Okay. This is the final expression, which is marked, highlighted in yellow. That is the graph. Both of them are really important. Let's write important over there also. This is also important. You must remember this graph. Okay. Next, when you're talking about the current decay, then this is the expression which has been highlighted, and this is the graph. Again, important. You must remember this. You know these graphs. A lot of questions are asked on this graph also. Again, here, how do you define the time constant? In this case, you will realize at t equals tau, at t equals tau, I would be 36.8% of n naught. So that is how you can define your time constant. That after every time constant, the current would have dropped by a factor of 1 by e, which you can clearly see from this expression. Okay, after 1 by after one time period, what will happen? The current would have been I naught over E. After two time constants, the current would have been I naught over E square. After three time constants, I naught over E cube, and so on. Okay. So this is the growth and decay of a current in LR circuits. Okay. Why don't we try a slightly tricky problem on this? So here, this is a typical question on this topic. So if you followed the derivation before, then you should be able to solve this. So this says that for the circuit shown in the figure, the EMF of the battery is 50 volt. Now R1 is 10 ohms, R2 is 20 ohms, R3 is 30 ohms. Okay, so these are the resistors. This is R1. Okay, this is R2. This is R3. Okay, and their values have been given to you as 10, 20, and 30. And the inductor has an inductance of 3 millihenry or 2 millihenry. You have to find the current through R1 and R2 in case A immediately after switch is closed. So that will be at t equals 0. Case B, a long time after S is closed. C, immediately after S is reopened. And D, long time after S is reopened. So I'll give you guys 1 or maybe 2 minutes to think about this. Okay, so think about this, try it, and let's see if you can figure this out. Okay. Go for it. And again, as I keep repeating myself, even if you're watching the recorded version of the video, you should still be trying. Use this time to try this problem and don't just wait to see the solution. Okay. So remember what I told you. How does the inductor behave? How does the inductor behave? Okay. How does the inductor behave at t equals 0? How does the inductor behave at steady state? Just remember that and you should be fine. Okay. Okay, I think 2 minutes are up. So does anybody have an answer? Do you would you like to share an answer? Okay, so many people watching, but nobody has an answer yet, which is strange. All right, no worries. Let's see what will happen. So immediately after the switch is open, let's this immediately after switch is. So you know what will happen. What was the current immediately before the switch was closed? The current in this branch was 0, right? So let's call this I1. So let's mark the currents. Let's call this I1. Let's call this I2. Let's call this I. Okay. So I'm assuming that at any time instant, these are the values of I currents through various branches. So now we know for part A, just before the switch was closed, I know was 0. So if I1 was 0 just before closing the switch, then just after closing the switch also it will be 0. That is what you need to remember. That is the most important property of an inductor. It cannot allow the current through it to change instantly. Okay. Therefore, just after just after closing the switch, also I1 will be 0. L behaves as infinite resistance. We had discussed this. At t equals 0, an inductor behaves as an infinite resistance. Right. So our inductor behaves as an infinite resistance. So no current flows through here. So all the current will flow through this. Okay, if the current is flowing through this, so now can I say how much will be I? So therefore, I would be equal to I2, and that would be equal to EMF over R1 plus R2. Correct? Yeah. So the current is only flowing through R1 and R2. So that will be the total resistance of the circuit. The inductor is behaving like an infinite resistance. So this branch does not receive any current, and this will be my answer. So we have to find the current through R1 and R2. Yes, this is my answer. Current through R1 will be equal to current through R2, which is equal to 50 over 30. Yeah. Yes. So immediately after closing the switch, the current is 1.67 ampere in both R1 and R2. Okay, so this was easy. And this is how easy the problems are going to be if you know the concept that is being used in solving this. Now, after a long time, next you've been asked, a long time after S is closed, a long time after S is closed, that will be the steady state. At steady state, how does the inductor behave? The inductor behaves as a resistanceless wire. In steady state, or t equals infinity, long time means they are trying to imply that t has almost become infinite. At steady state, is separate. L behaves as zero resistance wire. Right. So I can completely forget about the L in the circuit. If I forget about the L in the circuit, what is the circuit that I have? So for case B, I can say that this is what my circuit looks like. So you have R1 here, then you have R2 here, and you have R3 here. Right. So that is the trick of solving all these. At t equals 0, replace the inductor as an infinite resistance, or you can completely remove the branch having in the inductor, and at the steady state you can completely remove the inductor itself because it is nothing but a resistanceless wire. Okay, so this is the circuit at position B. So now we can easily see what is the total resistance of the circuit. The total resistance of the circuit, say that R equivalent of the circuit would be R1 plus R2 R3 over R3. Let's start writing the value. So that will be 10 plus 20 into 30 over 50 at 3 by 5. So 50 and 60, that will be 110 is 22. 22 ohms is the equivalent resistance. So therefore, what is I would have been 50 over 20 or 25 by 11 amps. Okay, so I is the current through R1. Next, what was asked of me? Next, I was asked to find the current through R2. So how about the current through R2? So there are two ways of doing this. You can say that okay, so I is coming from here, I1 going from here, and I2 going from here. If you remember that the current divides itself in inverse ratio of the resistances, then what you can say is that I2 would be equal to I times R3 over R. This is using the logic that the current would have divided itself in inverse ratio of the resistances. Okay. So I know the value of I. If I substitute all the other values, I will get I2. Okay. So that is how easily you can solve these circuit problems. Next, you have been asked what will be the current when S is reopened. Immediately after reopened. So immediately after reopened, you will realize that just as it is reopened, the current through the inductor cannot change. However, the current cannot go through R1 also. So you will see all the current would flow in this branch. And how much current will flow through this branch? I1 only. Where I1 would have been the current in the circuit just before this switch was reopened. So the current here, I2, I1, that will flow here. So for this, the answer would be R for I1 would be 0. Okay, so I can immediately write that I equals 0 and I2 would be equal to I1 initial, I1 of B, part B. Okay, and I1 of part B, that would have been I1 for part B would have been I of B times R3 or R2 over R2 over R2 plus R. Okay, again, using the fact that that current would have divided itself into inverse ratio of the resistance. Okay, so here it was, we were getting I times R3 over R2 plus R3. Here I would have gotten I times R2 over R2 plus R3. So that will be the current. How about long time after S is reopened? At this instant, you realize all the current would have decayed. So here the answer would be I equals I2 equals 0. All the current would have dropped down to 0. Okay, so this is how you will tackle a typical problem with an LR circuit. Okay. Remember, the current through the branch connected with the inductor can never change instantly, and use this fact. Also use the fact that at t equals 0, these uh, again at t equals 0 or just before or just after something, the current through the inductor branch does not change. So either it will behave as an infinite resistance, or at steady state it will behave as a zero resistance. Similarly, just after opening the switch, you have to realize what was the current before the switch was opened. When the switch was closed, what was the current? So the current through the inductor would have remained the same. Okay, so I hope you guys followed this. If any doubt about this solution, then you can let me know. Otherwise, we will move. Okay, so let me know quickly. I'll give you 1 minute to go over the solution, and let me know if you have any confusion. Okay, Rishabh. Wait a second. Okay, so what is case C? Case C is asking you what is the current through both these immediately after S is reopened. So this is coming after this. Okay, so once you had achieved the steady state. Okay, so let's consider the steady state circuit first. So let me maybe add a page in that. What the steady state circuit looks like. Okay, so at steady state, the circuit would have looked like this. You would have had a battery of EMF 50. Then you would have had R1, which was 10. You would have had R2, which was 20. And you would have had R3 and this inductor, which essentially behaves as a resistance-less wire. So at steady state, okay, so Sunila, just wait. The revision series, I think we are going to continue with Newton's laws. So we have only had one session for Newton's laws. We will have another session at least for Newton's laws. And after Newton's laws, I will move on to work, power, and energy. Okay. So I'm going in the sequence of the class 11 topics only. So kinematics, Newton's laws, work, power, energy, momentum, and then rigid body, then fluids, gravitation, and so on. And once we are done with class 11 topics, I will move on to the class 12 topics. Okay. So at steady state, we had just analyzed at the end of part B that current through here was 25 over 11. Okay. And this current would have divided into the ratios of 2 by 5 would have gone here. So let's just calculate those. So I1 was here and I2 was here. So I1 would have been 2 by 5 of I, which is 2 by 5 times 25 by 11. That is 10 by 11. 10 by 11 would have flown through this. 10 over 11 amperes would have been flowing through this. And similarly, I2 would have been 3 over 5. Inverse ratio of the resistances. Okay, the ratio of the resistance is 2 is to 3. So in one, you will have 2 by 5, another you would have 3 by 5. And it would be in the inverse ratio. From 20, you would have had 3 by 5. See? So here you would have had 15 by 11. Those would have been the currents just before the switch was reopened or when the steady state was achieved. Okay. Now imagine if you suddenly open this switch, if the switch here is open now. So when you open the switch, what will the circuit look like? There is a battery, but this is disconnected. Now you have this resistance which is hanging, you have this resistance, and you have this resistance, and you have the inductor. So what you will realize is that the current through this resistance will drop down to zero immediately. Why? Because this is a part of an open-ended circuit, right? This is not a part of any closed circuit. So the current here would immediately be zero. And this is no inductor attached to it. So nobody is stopping the current from falling to zero instantaneously. However, how about the current in this branch? The current in this branch cannot change instantaneously. It will remain 10 over 11. Just before it was 10 over 11, just after also it will remain 10 over 11 only. Because this current can never change instantaneously. How about the current through this? The current through this can change instantaneously. Okay, because this branch does not have a resistance. So what will happen is that this entire current of 10 over 11 would start to flow like this. Okay, did you get that? So the answer to part C is that I equals 0, which is R1 current becomes 0, and I2, which was R2 current, that would be 10 over 11 amperes. Do you follow this, Rishabh? Is it clear now? See, it's a very simple thing. Just draw the circuit just before something and just after something. And wherever the inductor is connected, in that branch, do not change the current. In every other branch, the currents can change instantaneously. That's it. Now, what will happen if I leave this circuit for a long, long time? If I leave this circuit for a long, long time, you would have realized that the current would have eventually decayed, right? All the energy stored in the inductor would have gotten dissipated across these two resistors, right? And at t equals infinity, this also would have become zero. What would have been the current equation for this? Right, I naught. This would have been the I naught of this circuit. And the time constant, what would have been the time constant? The total resistance would have been 20 plus 30, 50. So time constant would have been L over R. So tau for this second part would have been L over R2 plus R3. With this time constant, the current would have fallen. I would have been I naught times e to the power minus t over tau. This is the equation that would have happened after this switch was opened, after the case C has happened. At t equals infinity, you realize the I would have become 0. So the answer for D would be I equals 0 equals I. So currents across both R and R1 and R2 both would have dropped down to 0. Okay. I hope you followed that. Now, this is very simple, don't worry about it. Alright, why don't we try another question then? Let's try another question. So in this circuit, you have been told, in the circuit shown in the figure, find the current in the inductor as a function of time if switch S is closed at t equals 0. So at t equals 0, I'm closing the switch. You have to find the expression of current as a function of time. How does the current in the circuit or in the inductor changes as a function of time? In the inductor, you've been asked. You could have even derived the expression for current through the battery also as a function of time. We can do all that. So what do you think would be the expression? So give me all the expressions. Okay. Give me this I, give me this I1, and give me this I2 as functions of time. Okay. After that switch is closed. At t equals 0, you have to imagine all these were 0, and now the switch is closed. Okay, what will be these currents I, I1, and I2 as functions of time? Here, of course, you will have I again, correct? Okay, so try and give me the answer for this. So again, I'm taking up the tricky ones only. The easy ones I'm leaving for you. Okay, the simple ones, the straightforward ones. I hope once I've shown the derivation. So if there are too many resistors, what do? You find the R equivalent. Like in the last case, the tau would have been this for part C. Okay, so think about what will happen here. Here, things would be slightly different. Okay, so try and give this answer. So you can also let me know, by the way, by writing trying in the chat that you are trying. Okay. So I hope at least Rishabh must be trying this. So Rishabh can write trying in the chat to let me know. I don't know about the others. I would appreciate if all you guys tried this problem, but and if you could let me know that you're trying. Just write trying in the chat. This is a tricky one. So it's okay. It's okay. You just have to try. You don't have to get this right, but definitely try. Think about how you would have approached this. Okay. Okay. So that is 20 by 2 e to the power minus 1. 1 minus. Okay. So what is that? Which current is that? Which current are you talking about? I1 or I2? I think I2. Hmm? Do you mean I2? The current through the inductor? Hmm. That's all right. That's all right. You just have to try. Try if imagine if such a problem was thrown at you, how you would have approached it, and then we will see how you should have approached it. That's all right. Try and think of your because in the paper that is going to be the case, right? So this is the I. Okay. So Rishabh says that this is the so for I. I hope you remember how we used to analyze RC circuits. Do you remember that? You remember how we used to analyze RC circuits? If you remember that, then trust me, this would be easy. Hmm. Hello, Meet. How are you? Meet, are you in class 11th or 12th? I think you are a class 11 student, right? Yes, I am live. Okay, okay, all right. Tanya has also given an answer. 2.22, 1 minus e to the power minus 2.7 times t. Okay, maybe that may be correct. That does seem correct, in fact. Okay. So Tanya's answer does seem correct. So I'll tell you a small trick that I had told you in solving RC circuits. That is why I wanted you to try. I wanted to see how much you remember from RC circuits. I don't know if you remember this trick. There was a trick. Trick was the time constant. If you remember, for the charging circuit and the discharging circuit of an RC circuit was always the same. Right? So that is going to be the case here also. I is this. Okay. Okay. I'm not sure about that. So it maybe no, no. The power of E is wrong. Trick was the time constant for growth circuit. Current growth circuit is same as current decay as the decay circuit. So that's the trick. If you wanted to solve this quickly, then this is the trick that you should have used. So if you want to find the time constant for growth of current through this inductor, okay, so you know the current would be of the form that I or I2 would be equal to some I2 naught times 1 minus to the power minus t over tau. Has to have this form, right? Where I2 naught would be the steady state current, the final current. How do you find the steady state current? So for that, you replace the inductor by a resistanceless wire, right? I hope you remember that. I2 naught equals steady state current. That I can know. How do I know that? All I need to do is for steady state, I need to replace the inductor with a resistanceless wire. So let's try and find out the value of I2 naught first. So my circuit would have looked like this. So I would have had a 6 ohm resistor here, a 3 ohm resistor here, 4 ohm resistor here, and a battery here. This is the steady state circuit. Okay. Okay. So me it says in the reference, in the frame of reference, if frame of reference translated or rotated vector not change through component may change. Please help me understand this and this sentence right. No, that see, inherently there is something wrong with that sentence. I don't know. You've missed something. You're writing in the reference in the frame of reference. If frame of reference translated or rotated vector not changed, though component may change. Okay, I'm not sure what you're trying to say. Okay. I think I get you. Depends on what vector you're talking about. Depends on what vector you're talking about. Me. Some vectors are reference frame dependent. Some vectors are reference frame independent. For instance, if you're talking about your position vector, then position vector would definitely change, right? So I don't know what kind of vector are you talking about. If you talk about the force vector will not change. The components would change. The force obviously would appear exactly the same. Okay. So let's mark the resistances. So this was 6, 3, this was 4, and this was 20 volt. So first I'm showing you the shortcut. And if you're interested, I can show you the long method also for this. Ah, the power of the E is still wrong. Power of E is still wrong. So from here, I can find out that R equivalent for steady state circuit I2 not have to find. So let's just find the R equivalent first. R equivalent is 6 into 3 over 9 plus 4. So that is 6 ohms, right? So the current I for I would have been equal to 10 over 3 amperes, and I2, therefore I2 naught would have been equal to, so the ratio is 2 is to 1. Okay, so in this you would have had 2 by 3. Okay, the lesser the resistance, the more would be the current flowing. Force vector, yes, force vector will not change. Force vector will not change. If even if you translated your reference frame or rotated your reference frame. Okay, okay, I will. So let me just write the solution of this. So this is 20 by 6 or 20 by 9, which is roughly 2.22. Yes, all you guys got that right. Okay, just hang on. Now, how about the tau? If I can calculate the tau, then my job is done. I get the equation, right? And for tau, what do? I will use this trick. For tau, I will use this trick that time constant for growth circuit is same as that of decay circuit. So for finding the decay circuit time constant, all I need to do is replace the battery. And imagine now the current is decaying through all the resistances. Okay. So decay circuit looks like this. Let's draw you the decay circuit. This is what the decay circuit would be. So you would have had a 6 over here, 3 over here, this L over here, and 4 over here. So what is the R equivalent? You know the time constant here would have been tau would have been L over R equivalent. Okay. So R equivalent, you realize 6 and 4, they are in parallel. Okay, and this parallel resistance is in series with 3. So R equivalent dash, let's call it R equivalent dash, I can calculate as 6 into 4 over 10 plus 3. So that is 2.4 plus 3, that is 5.4. Okay. Now, this inductor had an inductance of 2 Henry. So this would be 2 over 5.4 or 1 over 2.7. So yes, the equation that you would have had is I2 would have been 2.22 into 1 minus e to the power of minus 1 over tau. 1 over tau would have been 2.7, so 2.70. This would have been the expression for I2. Okay, I hope you followed that. This is how you would have found the I2. I think Tanya had got this absolutely correct. So very well done. Yes, Tanya had this answer, exact answer. Okay. The position vector will change Meet. Okay, so let's get back to Meet's query. Add page here. Okay, so Meet, I will show both you guys both those things in a single diagram only. So imagine what is your reference frame? Reference frame is a set of coordinate axes with an imaginary observer, right? So this imagine is your reference frame. You have a y-axis, you have an x-axis, you have an origin O, and you have an observer, imaginary observer at O. Now also imagine that there was a particle of mass m, let's say here. Okay, so here was a mass m, and it is experiencing a force. It is experiencing a force of, let's say, in this direction only. So F, and what would this F be? It would be, let's say, 5 I cap. Okay, it is in the x direction and it has a magnitude of 5. Okay. Now imagine that what is the position vector of this? What is the position vector of this? Position vector of this would have been, let's say that this is x1, this is y1. The position vector of m, which is this, can I say r vector would be x1 I cap plus y1 j cap, right? Now imagine if your reference frame translated. Okay, your reference frame shifted. Let's say it shifted here. The origin shifted here. This is you translating the reference frame. And it shifts by some x0. Right. So now you realize what is this? The x coordinate becomes x1 minus x0. Right. The y coordinate still remains the same. So in the new reference frame, let's call this y dash x dash. In the new reference frame, what is my position vector? Position vector r dash would be x1 minus x naught I cap plus y1 j cap. Right. How about this? How about this? The force vector remains the same, obviously. It is the force is still represented by this vector, right? That does not change. It will, in this case, it will still be 5 I cap. In this case, even the components do not change. Okay, as long as you are only translating. If you rotated the reference frame, then the components would have changed. Okay, so imagine instead of this, if you now rotated your reference frame. Okay, so choose some other color for a rotated reference frame. So let's say you made it like this. Okay, so this is y double dash and this is x double dash. Now you will realize that the position vector would have again changed. Position vector would have been, in fact, r double dash vector. That would have been, let's say this length would be x1 square plus y1 square root, okay, times I cap. Okay, I will just explain to you. So position vector would have been root of x1 square plus y1 square times I cap, right? Similarly, you would have realized now the components of the force vector would have changed, but the force vector itself would remain the same. Force vector would still be pointing in this direction and would still have a magnitude of 5, right? This does not change. This does not change. The force vector does not change. Its components have changed in my reference frame. Okay, I hope you followed this myth, and I hope I have been able to answer your query. Okay, yes, Suraj. So see, for finding the decay circuit, you just remove the battery. Imagine that whatever was powering the circuit initially, later that battery power source has been removed, and rest of the circuit is where the inductor is providing all the power. Okay. Now this is the decay circuit. Okay. Are you fine with this? That this is what the decay circuit will look like. I all I need to do was remove the battery. Okay. So once I remove the battery, now let's see. Now what is happening is that inductor behaves as a battery in the decay circuit, right? In the decay circuit, imagine instead of the inductor there was a battery. Now what do you see for this battery circuit? Do you realize that 6 and 4 are in parallel with each other and they are in series with 3? Okay, one problem at a time. So imagine that there was a battery instead of an inductor. And what would have been the R equivalent of the circuit? Okay, so R equivalent of the circuit would be the equivalent resistance between these 2 points, right? I hope you followed that. So when judging the R equivalent of decay circuit, always remove the initial power source, treat the inductor as the battery. Okay, great. So yes, Smith was saying, sir, how force component change? Okay, so you realize if I rotated my axis, then you realize this was earlier in I cap. Now it will have two components. Let's imagine that this was theta. Then now this would be like this. The force vector would have two components. Agreed. So now what is F double dash? In the reference frame of double dash, F double dash would be represented as F cos 5 cos theta I cap and minus sines 5 sin theta j cap, right? As opposed to 5 I cap initially. So initially the I component was 5, j component was 0. Now you will see you have an I component and a j component. So the components have changed. However, what about the total vector? The total vector still points in that same direction, still has the same magnitude. So the vector has not changed. How do you define a vector? A vector is defined with the help of its magnitude and its direction. Okay. So since neither the magnitude changed nor the direction changed, so the vector does not change. However, because your axis has changed, so because of which those ij components would change. Got it? Is that clear? Let me know. Uh, okay. I don't know what you meant to say, so I don't know how to correct it. Uh, so you can say that if the reference frame translates or rotates, then uh, again some vectors are frame dependent, some vectors are frame independent. So there is not a consistent statement. As you know that velocity is a frame dependent vector, right? Velocity vector depends on your reference frame. So if your reference frame starts to translate, velocity will appear to be different. So what vector are you talking about? It matters. So force vector, that never changes with your reference frame. That is a frame independent vector. Okay. Similarly, displacement vector would be the same irrespective of what your no, that will depend on the reference frame also. So displacement vector, position vector, all these will depend on your reference frame. Velocity vector. Okay. Force is a vector which does not depend on. And I can think of other vectors which would be frame independent. So very few quantities which are frame independent. Most of the quantities depend on the frames. Yeah, so force is the only one which I can think right now. Okay. All right. So I'm sure. Okay. So this I had initially planned to discuss combination of inductors, but then I realized we also have to take a mutual induction into consideration. So we will discuss this EMI. Okay. Mm, okay. Meet meet. See, velocity vector is defined as rate of change of position vector. If your position vector is different, the velocity vector would also be different, right? I hope you realize that. Okay. In the reference frame of yx, m may appear to be stationary if it is not changing its position. But if your reference frame is translating to y dash x dash, then it will appear that it has a velocity. So velocity is definitely frame independent. Agreed. That is what I'm saying. Okay. So this we will take up after mutual induction. We will discuss after mutual induction. After mutual induction, we will take a combination of inductors. Okay. By the way, there was a long way also of solving this problem. So this is a shortcut. Okay. Once you know this, you can find the currents in other branches also. Okay. All right. So the longer method was, this question can also be solved using your KCL KVL. That would be a long method. Write those differential equations of KVL and KCL, okay, and then integrate those, and then you would have gotten. Yes, Meet. I think I told you. Imagine, no. Imagine that this is a reference frame. Okay, if this is a reference frame, a particle is here. In this reference frame, its velocity is zero. Now, if the reference frame starts to move like this, then in the reference frame, the particle is coming like this. So in a moving reference frame, the same particle will have a velocity. Okay, so velocities also depend on the reference frames. Okay, yes. So, okay, combination we will talk about later. Let's just quickly go over mutual inductance and the phenomena. What is that? So mutual inductance involves interaction of one coil's magnetic field with another coil and induction of an EMF in the adjacent coil due to variation in the current of another. So in self-induction, we realized that there is an EMF that is getting induced because the current in one coil is changing, due to which the magnetic field produced by that coil is changing, and that change of magnetic flux of its own current is causing an induction of EMF. In mutual induction, what is happening is that you have two coils which you have close by. So let's say that this is coil number one, and you have another coil just close to this. Let's say you have coil number two like this. Okay, so this, imagine, does not have any power source, and this guy has some power source attached to it, and some other mechanism by which you are changing the current. Maybe a variable voltage battery is there. You can change the voltage of this battery and vary the current. Now, what you will realize is that when the current is flowing through primary coil, this is called the primary coil, and this is called the secondary coil. Okay, so when the current is flowing through the primary coil, it is producing a magnetic field in the primary coil, right? Now, some of this magnetic field will pass through the secondary coil also. So you realize, because of the current of primary coil, there is a magnetic flux that is getting linked to the secondary coil. Now, if I vary the current in the primary coil, the magnetic flux linked with the secondary coil also changes, and this will induce an EMF in the secondary coil. This is known as mutual induction. So induction of EMF in one coil due to variation in current of another. Self was induction of EMF in one coil due to variation in current of its own. Okay, so this is how it is different from mutual induction. So mutual induction, self-induction. Mutual induction, in fact, involves interaction of one coil's magnetic field with another coil. Okay, I hope you followed this. Now, mutual induction is the basic operating principle for transformers, motors, and a lot of generators and other electrical components that interact with another magnetic field. Okay, so we will study about transformers. So major use of this mutual induction is in transformers. Okay, we will study that after we have studied AC, alternating current. Now let's assume that the flux linked to second coil is phi 2. So I'm assuming that whatever the flux linkage is happening here, this is phi 2. Now, can I say that this phi 2 would be directly proportional to the current of coil number 1? So if in coil number one, imagine if the current was flowing as I, so you realize whatever this magnetic field is being produced, whatever this magnetic field is being produced, I hope you remember that this B would be proportional to I, right? How about phi 2? I can now say that phi 2 would have been proportional to B. The more the magnetic field, the higher would have been the flux linkage. So therefore, what I will conclude is, so let's call this I1. So let's keep it to I1. So therefore, I can say that phi 2 would also be proportional to I1. So this is the logic of me saying that the flux linked with coil number 2 would be directly proportional to the current in coil number 1. Okay. So if I introduce a proportionality constant, I get phi 2 equals m times I1, where m is called the coefficient of mutual induction. So this, you realize, would appear very, very similar to coefficient of self-induction. There also, if you realize, we had said about this, we had talked about this, we said that phi of any coil would be directly proportional to I of that coil. Here, the difference is that phi through one coil is proportional to I of the other coil. Okay, and the proportionality constant is called the coefficient of mutual induction of the two. Now, let's just quickly talk about mutual induction for like 2-3 minutes, and then I'll wrap up today's session. Okay. Now, the coefficient of mutual induction depends on the dimensions of the coils and the separation between the two coils. It will depend on the dimensions and the separation and or the relative positioning of the two coils. So you realize if I keep these coils very, very close, then the flux linkage would be higher. If I keep these very, very far, then the flux linkage would almost be zero. So the value of M is depending on the relative positioning and also the size. Imagine if this was one coil and I had a huge coil which is completely surrounding this, then the entire magnetic field would be linked with the outer coil also. So it depends on the dimensions and as well as the relative positioning of the two coils. Okay. Now, interestingly enough, M is a bidirectional coefficient which remains same for a given pair of coils, and it can be used in calculation of flux linked with either coil due to the other. So what here I'm trying to say is that imagine if here, if I wanted to write phi 2 and I will write it as phi 2 being equal to m of 2 due to 1 times I1. So M21 is the mutual induction coefficient of 2 with respect to 1. Then if I did the other thing, which means if instead of flowing a current through coil number 1, if I flew a current through coil number 2, then what will happen? So if I2 current was flown through coil 2, then you would have realized that phi in 1 would have been equal to some M12 times I2, sorry, right, where M12 is called the mutual induction coefficient of coil 1 with respect to 2. Now, turns out that M12 is always equal to M21, which can be replaced as M pi, because both are depending on the relative sizes and relative positionings. So once that is fixed, then you will realize that it doesn't matter. It doesn't matter which coil has the current. The flux link would be proportional to the currents, and the proportionality constant would be the same for either of the two. We will prove that also in an example that we will take. So this is known as the reciprocity theorem. Okay, please remember, this is important. That for two coils, the coefficient of linkage of flux or the mutual coefficient of mutual induction is same. Okay, so M12 is always equal to M21. So also, this is a scalar quantity, of course, and will also have the SI unit of Henry only, because this has exactly the same dimensions as that of the self-induction coefficient L. I hope you remember that. That here also I can define M as pi over I. Okay. So since it is the ratio of flux to current, the units are same, Henry, and that is where I will wrap up today's session. We will discuss this problem in the next class. Okay. And this is where I would like to wrap it up for today. We are running out of time. And before I leave you, let me remind you of one last thing, that if you haven't gotten your Unacademy subscriptions, Do it quickly, and this is how you do it. Install the Unacademy app, go to the plus section of your app, select your goal as IIT and click on that get subscription. Use this code RDLive to get your subscriptions and enjoy a 10% off on already very, very competitive and fair pricing. Okay. This is a list of 3 ongoing courses for class 11 topics or topics aimed for the JEE Mains and Advanced 2022. And there are 4 more courses for class 12 topics. So you can get yourself the Unacademy subscription and enroll in these courses as soon as possible. Now, if you like today's video, if you think I taught you something new, again, I helped you learn something new, don't forget to press the like button and also share this video with all your. As I keep telling you, that for those students who can't afford the Unacademy subscription, Unacademy is happy to provide quality free education also. So again, see, this channel was started so that the language should not be a barrier for learning of a student. Similarly, even monetary conditions should not be a barrier towards learning of a student. So we want everybody, if they can afford the subscription, definitely better for them. But even if you can't afford, Unacademy is happy to help and would like you to keep studying, following us on YouTube. And to make that happen, you need to share it with as many people as you can so that everybody who needs this should get this. Okay. Again, don't forget to press the bell icon, and the PDF of all the slides and used in today's lecture would be available for download very, very soon. Also, let me remind you that the next Unacademy Combat event is going to be happening live on 22nd of November. You can enroll in that using the code RDLive and do well, win yourself some prizes. Okay. Another reminder of, those of you who are following us on the JEE English channel of YouTube should be connecting with us on the Telegram app using this link so that you're not missing out on any of the lectures or sessions happening on the JEE English channel. Finally, before I leave you, one last reminder, RDLive is the code that you want to use if you like my lectures. If you'd like to enroll in my courses on Plus, make sure you're getting your Unacademy subscriptions with this RDLive course and enjoy a 10% off on all your futures. All right, so that is it for my side today. We will continue this discussion now next week because, as you know, now we are only hosting 2 sessions per week for class 11th and 12th students, and 3 days a week I have started a revision course. Okay, so we will carry forward this discussion on Tuesday, where we will discuss more about mutual induction and about combination of inductors. Okay, so you guys keep studying, go through the notes, go through the lecture. If you have any doubts, you can either leave your doubts in the comment section or bring them up in the next class live. Right. So I'll see you next Tuesday now. So till